So this project is focused on parallelizing the collaborative filtering system used, an inspiration for this is drawn from the Netflix challenge. So a little background on the Netflix challenge itself. So back in 2006, Netflix proposed an open competition for anyone to enter to improve their own recommendation algorithm. And I'm assuming most people are familiar with Netflix's recommendations system, but basically it recommends you shows or movies based on things you have previously watched. And the main idea and intuition behind how Netflix does this is something called collaborative filtering, which we'll get into more detail to later. But essentially the challenge was to improve Netflix's own collaborative filtering algorithm. So competitors were given a data set of over 100 million user ratings, which consisted of ratings from over 480,000 users that were given to around 17,000 movies. And so competitors were to build a collaborative filtering model based on this training data set. And then how they were evaluating the models were the judges had their own data set used for testing that would measure the accuracy of the competitors' models. And so this data set was hidden from the competitors, and this was used to evaluate it. And they also used the root mean squared error metric to predict. They used the root mean squared error defining metric in order to evaluate the accuracy. So in the end, in 2009, a team called Belcour's Pragmatic Chaos team came up with a solution that actually bested Netflix's own algorithm at the time by 10.09%. And so they ended up winning the $1 million prize. And so also an important note here is that our project is mainly focused on how do we parallelize collaborative filtering and the collaborative filtering algorithms that go into it, not on improving the accuracy of the model itself. So to begin, we'll talk about discussing what recommendation systems actually are. So I'm sure we've all been exposed to recommendation systems some way or another, whether that's through accessing applications like YouTube, Spotify, or Amazon or eBay, which recommend content, as well as social media sites like Facebook. So the main idea of recommendation systems is that they try to predict what a user would rate an item and then recommend products and or content based on those predictions. Recommendation systems not only enhance user experience, but also increase user satisfaction and then drive sales for new products. And they can keep users using your service longer. So if you keep recommending them new products to buy or new content to consume, they will want to keep using your service or keep buying more products. And recommendation systems function using two kinds of information. The first one is information that characterizes products, which would be content-based. For example, Amazon recommends products similar to the ones that you've purchased or viewed. And then the other information that recommender systems function on is user item interactions. So this is what we will be focusing on, since this is what collaborative filtering is based on. So the main idea behind collaborative filtering is, we'll start off with a simple example. So say this is me, I like pizza and salad, and my friend Bob also likes pizza and salad, as well as soda. So based on our similar likings of pizza and salad, I may also like soda. And then the recommender system would recommend this product to me. So the intuition behind collaborative filtering is that it takes information from thousands of users and uses it to predict what I would like based on people with similar interests to me. just as kind of a breakdown of what we'll be discussing during this background section, I've already talked about what recommender systems are, and then collaborative filtering techniques in the context of recommender systems. We'll also be discussing matrix factorization, which is a technique for collaborative filtering, and then we will further go down into discussing alternating least squares, which is an algorithm for matrix factorization. And so we will be discussing the basics behind this algorithm as well. So collaborative filtering, as mentioned before, it can be broken down into memory-based and model-based. Memory-based calculates similarity between two users and then bases predictions from those similarities. However, problems with this lie in the fact that memory-based collaborative filtering may have biases towards certain products that have either been rated a lot or just more popular in general. So a product might be recommended simply because it's popular, not because it holds relevance to that user. On the other hand, model-based collaborative filtering trains a machine learning model. And we represent ratings from users for specific movies in the context of the Netflix challenge. It's represented by a matrix with users as rows and then movies as columns. However, the main problem here lies in the fact that not every user has rated every movie. So this leads to a matrix that looks similar to this. So a really sparse matrix that our goal is to fill in. So how do we learn the missing values of this or predict the user ratings of those unrated items in the matrix in order to come up with accurate predictions for a new user? We can solve this problem known as the sparse data problem using a technique called matrix factorization. Matrix factorization is a well-known algorithm for collaborative filtering. It has been increased in popularity from the Netflix challenge, and it focuses on dimensional reduction. So in the case of a user item matrix, the two dimensions as seen here are the users and the items, or movies in our case. And basically, from decomposing this big user item matrix into these separate matrices, you can then take the dot product of a user and an item to find ratings that were given or predicted by the model. Additionally, both the user and the item matrix have what are called latent features, also known as hidden features. So this represents the amount of abstract information that is stored in this lower dimensional space. More latent features leads to a greater personalization. However, we don't want too many latent features because then the model will start to overfit. So we can fine-tune this parameter along with another parameter that prevents overfitting called regularization parameter in order to come up with a model that has optimally tuned hyperparameters for the problem we are trying to solve. And then here's just another more generic view of matrix factorization. As mentioned before, it solves our problem of the sparse data, and it breaks down matrices into a factor of its products. So one of the main algorithms, as mentioned previously, is called alternating least squares. And this is what will be the main focus for our program. The goal of alternating least squares, like most machine learning problems, is to minimize a cost function. So as seen here, this is a cost function that we are hoping to minimize, and this represents user matrix and item or movie matrix. So the goal of ALS is to minimize the distance between actual ratings and then those ratings that are predicted. And so what ALS does is it first fixes a user matrix and then solves for the item matrix, and then fixes the item matrix and solves for the user matrix. So that's where the namesake comes from. So it does this in an alternating fashion. So when we do this, something interesting comes up. When we fix one matrix and optimize the other, the problem actually turns into a simple linear regression problem. And inherently, ALS is a two-step iterative process that alternates between these two linear regression problems, and hence the name alternating least squares. Additionally, For each computation, as seen here in the pseudocode of the algorithm, for each row of either a user or item matrix, it solves the least squares subproblem and then updates a matrix. However, since each computation of either a row of the user or item matrix doesn't depend on any other rows of the matrix, they can be solved independently, which leads to a massive amount of potential parallelization. And this is what will be discussed in the next section.
There were multiple teams that competed in the Netflix challenge, and one of them created a solution that we're going to look at here. It was developed by Zhao, Wilkinson, Schreiber, and Pan, and this was built off of collaborative filtering. Now, they used very similar approaches to what Marissa talked about before, like they used alternating least squares, but they did make some changes. They used weighted lambda regularization instead of matrix factorization. Weighted lambda regularization they use specifically to fix the sparseness of data, and they also used it just like matrix factorization, but they also used it because they wanted to fix an overfitting problem. Overfitting, you can see in the graph to the right over here. Basically, what overfitting is when the predictions that the computer makes are too close to the actual data, and they aren't going to give accurate predictions. So with this graph, you can see with the crest and falls, if you get too close to the data, you're going to get a prediction that's completely out of whack and won't really help anyone. So what you did, lambda regularization, is helped you to narrow down and get to a more accurate prediction. Now, singular value decomposition is something they also used, and this also helps with this. So this helps to get rid of some of the data that you necessarily, it might be stray, and helps you to get a more accurate prediction. Now, this solution had a root mean squared error of 0.8985, which was 5.96% better than what Netflix's RMS root mean squared error was. This isn't amazing given the original was a 10 over 10% like Marissa said, but this is still a good solution. Now, another work was which was done by Kevin Lau. Now, this work was more uses more of the concepts that Marissa brought up. It uses alternating least squares and matrix factorization instead of weighted lambda factorization and singular value decomposition. Now, this approach fixes a couple of problems that Kevin pointed out. Popularity bias, item cold start, and scalability issues. So popularity bias is something Marissa actually talked about earlier. Popularity bias is, let's say we're talking about like a movie being recommended in Netflix. If a lot of people look at this movie and it's really popular, then popularity bias means it's going to be recommended to everyone, regardless of if they actually be interested or not. It's a popular thing, so you must like it. Item cold start's kind of the opposite. It's where there's not a lot of data for a movie, so not a lot of interaction, not a lot of people have watched it, and because of that, no one's recommended it. Despite the fact that this could be a great movie, it's just that no one's watched it. So they're kind of two polar opposites. And then scalability issues. These are issues where basically the program couldn't take in a massive amount of data. Now, this program started off with collaborative filtering also. And as I said, they used the alternating least squares and matrix factorization that Marissa talked about earlier. And these were able to fix all these problems. Now, our group ended up developing our own solution, which I'm going to talk about in a second. And this solution was inspired by what Kevin did. So Dr. Shang gave us two files. He gave us a ratemovies.py and recommendations.py. Ratemovies.py is used to read movie ratings in and then to write those values, the ratings, into a file that's called that is in a CSV format. And we did not see a ton of great chances for parallelization here. The recommendations.py takes in those ratings from the CSV format file and then reads them in and then takes in them in and gives recommendations. Sorry about the little sputter. Now, the main problem with these is that we didn't see a great chance for parallelization either of them, so we ended up making our own solution. Now, our solution, as I referenced earlier, was heavily inspired by Kevin. It uses matrix factorization and alternating least squares. And I'm going to just walk you through what the basics of our new solution does. And there's a flow chart to the right to help you a little bit. So what it just starts off, it loads in the basic settings. It's going to need PySpark, Spark, and so on. And after that, the data is read in twice. And I'll explain why it's read in twice in a second. So first, the data is read in from a CSV file, from the CSV file. And it creates a temporary SQL table. The reason why it does this is so that we can query through the data faster. After that, it's reread, and it's split into two matrices. A matrix for the movies and a matrix for the users. And these are matrices that obviously are for the ratings, just for the movies and the users. And we do this so we can use it for the matrix factorization. After that, they are parallelized using alternating least squares. We will get into the parallelization in just a bit. And after that, they are run through different models and tested. And this is to help us see how accurate our program is and generate things like the root mean squared error. Then after that, we make recommendations for like a user or so on. Now, let's talk about a little bit about parallelization.
Now I will discuss the potential methods for parallelization in the current solution. So the first avenue for parallelization is through Apache Spark's implementation of ALS matrix factorization in PySpark. Currently in the solution, we are already utilizing Spark data frames in the ALS train function from PySpark. The ratings, movies, links, and tags datasets are all loaded in directly from CSVs into Spark data frames through the Spark read load function. The ALS training function is already also used to train each ALS model against the movies and user ratings. Now Spark already natively adds parallelizations to the ALS model fitting and prediction task by distributing tasks across different worker nodes inside of the cluster. Therefore, there isn't too much that we can do besides potentially looking into implementing our own version of ALS and parallelizing it from scratch. The next avenue for parallelization is MPI. Python contains a message passing interface library that can add parallelization by allowing processes to communicate with each other. Unfortunately, due to the nature of this task, MPI is not really being planned to be used. The large number of time will be spent by the ALS model training during the script, which is already parallelized by Spark and will not be further distributed across multiple processes. Finally, we have multiprocessing. Python contains another multiprocessing library that will allow us to add thread pools to the solution. The library allows us to create concurrent threads of execution and will be the primary form of parallelization that we will add to the initial solution. The first area for parallelization is in the train_ALS function. This is where we will be training the models and fine-tuning the hyperparameters. Inside of the initial function, there's a nested for loop that first iterates through an array of ranks and then iterates through an array of regularization values. Using the multiprocessing library, we can create concurrent threads and assign each thread a rank value to test. Our solution, shown on the right, will separate the train_ALS function into two separate functions to allow for parallelization, train_ALS and find_model. Find_model will be the base function and will create concurrent function calls of train_ALS, which is seen in the line where we set errors and models equal to the pool.apply function. Pool.apply will allow us to pass arguments to distributed calls of train_ALS. Train_ALS will find and return the best model for that process's assigned ranks against different regularization values, and find_model will find the best model from the returned models. Our next avenue for parallelization is in the getMovieID method. We also plan to use the multiprocessing library here, in the same way that we did in the train_ALS function. The starting function of getMovieID iterates through the list of a user's favorite movies and looks for those movie IDs of those favorite movies inside of the movie ID list. In the same way as the train_ALS function becomes parallelized, we'll be splitting the original function into two functions, getMovieID and getMovies. GetMovies takes in a certain movie and then grabs that movie IDs from the movie ID list and returns a list of that movie ID. In the getMovieID function, it takes all the return arrays the movie IDs and flats it into a singular list. As mentioned in the first slide of parallelization methods, PySpark already attempts to parallelize ALS trainings and predictions, but it may be worthwhile to look into implementing ALS from scratch. It's possible to parallelize ALS further by distributing the process that handles the updating of the user and item matrices. The potential speedup would be dependent on the size of the matrix, specifically the number of rows and columns in both matrices. Now I will discuss our evaluation methods, the job environment, as well as the tasks we plan on running. We do plan to run our jobs on Beocat, which we hope will maintain a high level of consistency through specifying shell script parameters. And to reiterate our previous point for evaluation, our proposal is focused on adding parallelizations to the existing code rather than improving on the collaborative filtering algorithm and its results. Therefore, our metrics will be speedups, efficiency, and memory usage rather than algorithm accuracy. Our tools for measuring those metrics include a Python script profiler, a Python library for process and system monitoring, and a Python time module for execution time measuring. Now to discuss how we are planning to control our shell scripts and their environment. For consistency, we will be using Beocat nodes confined to the ELSE node cluster, which has the following specs. A 2x8 core Xeon E5-2690 CPU with a 2.90 GHz base core clock frequency and 20 MB of Intel Smart Cache. And on those machines, they have installed SenseOS Linux 7, Linux version 3.10.0, Python 3.7, and Spark 3.0. Next, I will discuss the profiler that we use as well as the information that we received from the profiler. We were able to use the cprofile Python library module to define the time distribution across functions in the initial solution. As seen in the image shown on the right, the majority of the time is spent during the train ALS and train functions. The train ALS function is one that takes up the most time and is the one that we plan on parallelizing, as seen in the implementation section. It also is the function that makes the calls to train. Although we are unable to further parallelize the train function, as mentioned before, due to it being part of the PySpark library, we expect at least linear time improvements from the parallelization of the train ALS function as it calls the train function in parallel. Our implementation section also addressed the parallelization of the getMovieID function, but that function is called only once, and the primary data frame that would affect time in the getMovieID function is movies. So changing the number of ratings is how we're changing the data sets, so really should not be affected. Therefore, we expect minimal time improvements from the parallelization of getMovieID. After finalizing the parallelized version of our solution, we plan to rerun the profiler and compare the time distributions. Now I'll talk about the tests. So as the profiler showed time distribution, we're going to be using the psutil library, which is a Python library, for process and system monitoring to measure CPU efficiency, memory usage, and network usage. Then we will be using the time module to record execution time. We plan to further specify the shell scripts arguments on Beocat as well, to measure the benefits between using multiple machines and multiple cores per machine. The variation of number of machines and number of cores is shown in the image on the right, where it ranges from 1 node to 16 nodes and 1 core to 64 cores. Each test variation will be run with those different number of nodes and different number of cores, as well as different dataset sizes of ratings. So 100,000, 1 million, 10 million, and 25 million ratings. Now the ratings are what changes the training function, but would not affect the getMovieID function as previously mentioned. We will also be running the tests as array jobs of size 3 to ensure that there are no uncaught outliers in the results. In conclusion, our proposal provides an outline for a parallelized implementation of a collaborative filtering algorithm for the Netflix challenge. Our parallelization will include distributing the processes that fine-tunes hyperparameters for the PySpark ALS function across different nodes and different cores. We hypothesized that we can achieve linear speedup by the parallelization of the fine-tuning and potentially more linear speedups from the parallelized implementation of ALS if we can create it from scratch. Our jobs will run on Beocat and will measure execution time, CPU efficiency, memory usage, and network usage across various tests utilizing different number of machines, cores, and dataset sizes. Thank you.